We've talked about the fact that it doesn't really matter whether we use the conventional current where we pretend positive charges are doing the moving, or we use the real physical current where electrons do the moving in a solid. That's generally true, except there is one effect that will determine which one is really moving. Now, since we already know about the atomic theory of matter, this is not going to be a big surprise to us, but we're going to see how we figure it out. Uh, so this is the first time where it matters whether positive charges are carrying the current or negative charges. Let's look at the simple picture below where we have a battery and we've just got it carrying current around a circuit. Only here, instead of a regular wire, let's use a big flat sheet of metal like a baking sheet. And we'll say there's a magnetic field going into the screen through the sheet. From the way the battery's set up, the conventional current, positive charges, would go like this, clockwise. Right? We know that. If we do that, when those positive charges moving down get to this area where the field points into the page, take the fingers of your right hand, point them down, and then curl them into the page, and you'll see your right thumb points off to the right. So these positive charges are going to be pushed over here on this side. Now, once some of them build up over here, they're going to build up their own electric field, which will let the other ones just go right through. But we'll have positive charges on this side of the sheet. Now, what if instead negative charges are carrying the current? They're going to leave from the bottom of the battery and they're going to go counterclockwise. When a negative charge gets here, it's moving up. You curl your fingers into the page. Your thumb would point this way, but because it's negative, the negative charges get pushed to the right. Again, this is exactly what happened to the positive charges. So whatever is carrying the current is going to be pushed to the right. What do we do to figure out which one is sitting on the right? We actually connect a voltmeter. If the right-hand side is at a higher potential than the left-hand side, that means the charge carriers are positive. If it's at a lower potential, the charge carriers are negative. Now, it would be reasonable to think, okay, we weren't really surprised by this, but it was probably important to do the experiment. Now we've proved it. Now we're done. You can put it in a science museum. Turns out, though, it's very useful to be able to detect a magnetic field with this. Notice there's no external ferromagnet involved and no moving parts. And we can use this to detect whether there's a magnetic field going through this sheet or not, because we look and see if a potential builds up across it. Chips that can do this are called Hall effect chips, no big surprise, and they're pretty cheap. They can be $1 each or less, and they can be much smaller than you might expect. They are in a lot of different consumer products, including iPhones and iPads. The old flip phones where you would open them up and they would wake up, and maybe the new flip phones, I don't know, the new ones that are with the fancy bendable screen, it needs to know whether you've opened it or not. And this is done by having a magnet on one side and a Hall chip on the other side. These can also be used to count the teeth in a gear as the gear rolls around when they move past a Hall sensor to see how much a motor is rotated or if it in fact has moved at all.